All right, so I first want to thank Otter for putting on this last minute JMM substitute and giving everyone the chance to talk about their research. So what I want to talk about is a summary of some of the results from a paper that I recently uploaded to the archive. And that paper is called Optimal Polynomial Approximants in LP. So for this talk, I broke it into three sections. The first section I want to talk about is first section is an introduction. I just want to lay down some basic definitions and the motivation for why I chose this project. In section two, I want to talk about some results regarding the zeros of these polynomials. And in section one, I'll talk about the reason why I think location of zeros is something of interest. And also, I think more importantly, in section two, I'll present a conjecture that I've been working on. And one of my goals for this talk is to get some people interested in this conjecture as well, so that you can join me in trying to resolve it. Section three is a technique where you could study optimal polynomial approximants in the LP setting by using the Hilbert space setting of L2. And that's by relating an optimal polynomial approximate or equating it to a polynomial in L2. So I'll also talk about a conjecture in section three that relates to the conjecture from section two. And I think they're both worth investigating. So hopefully you feel the same way as well. So one of the original contexts for optimal polynomial approximants was the Hardy space H2, and it was introduced in this context in the early 80s. But just to recall what the H2 is, the Hardy space H2 is the collection of functions that are analytic in the disk so that this supremum is finite. And that supremum defines the norm on the function f. So in this context, what exactly is an optimal polynomial approximate? Well, you choose any f in H2 in any integer n. The polynomial capital Q, which that minimizes this norm, is called the nth OPA of 1 over f. And so we're minimizing the difference qf minus 1, where little q ranges over this set Pn, which Pn is the collection of polynomials of degree at most n. And one thing to note, we are in the Hilbert space setting, so existence and uniqueness is not too difficult to see. We have tools such as orthogonal projections. So the orthogonal projection of the function 1 onto the finite dimensional space Fpn gives us some function capital Qf. So we have existence because of finite dimensionality, but we also have uniqueness simply because f is not identically 0. And so OPAs, or optimal polynomial approximants, were originally introduced in this context to solve problems in one-dimensional signal processing, more specifically the design of one-dimensional digital filters. So I'm not going to talk about filters at all in this talk, but I do want to just mention the design process briefly. So the whole idea behind a digital filter is you have some kind of system that relies on input, and our whole goal is to modify that input in such a way that the output meets some given specifications. And the output is generally some type of sampling sequence of real numbers, and the input and output are usually related or can be related with by a difference equation. So often in studying these systems, you'll use Z-transform methods to take all the sequences involved and convert the sequences into functions of a complex variable. And consequently, the input and the output are related by some rational function. So that rational function which relates the input and output is called the digital filter for the system. And so the engineer's goal would be to design this rational function in such a way that the magnitude meets some given specifications. But in this theoretical context, there's difficulty in practice because when you go backwards and use the inverse Z transform, it's plausible that when your system's being subjected to bounded input, your output could possibly blow up. So in order to avoid this uncomfortable situation, you want to impose the condition that the denominator is zero free in the closed disk. This denominator Q. So in the case that that happens, you would say that either the filter is stable or BIBO stable, or the system is BIBO stable. BIBO just stands for bounded input, bounded output. So how does this relate to optimal polynomial approximants at all? Well, in the early 80s, Shui and Chan published a paper relating optimal polynomial approximants to the design of these filters. And the reason why they decided to use optimal polynomial approximants is because of this fact that they proved. They showed that for any function in H2 that doesn't vanish at the origin in any integer n, the nth OPA of 1 over f has no zeros in the closed disk. And it turns out that these optimal polynomial approximants are very easy to compute, so that was another reason why they chose. But at any rate, these OPAs are zero free in the closed disk, so then you can, at the very least, use them as this OPA Q as a denominator in this rational function so that you can guarantee that the system is stable. And so this summarizes a talk that I've previously given a few times on optimal polynomial approximants in signal processing. And there's always somebody at the end of the talk that asks me what happens to the filtering effects when you change the norm. Because that's actually a good question, because keep in mind this function, if we're using optimal polynomial approximants as our Q, then that function depends on the H2 norm. So if you change the norm, you change the function. If you change the function, you're changing the filter. So how does the filtering effects change when you switch from the H2 norm to something else? So something's going to change, but a better question is BIBO stability still preserved? So that motivated this project. So what happens to the filter when you change the norm? Is stability preserved? So to answer that question, I decided to go and investigate the LP setting. So recall that the space LP is the collection of measurable functions defined on the unit circle so that this integral is finite. And this integral defines this norm, and keep in mind, I'm only talking about P from 1 to infinity, and the reason for that is because I want to remain in the Banach space setting. Okay, so I'm considering this setting, but now what is the optimal polynomial approximate in this setting? So just like I did before, I'm fixing an arbitrary f, but also an arbitrary g in order to maintain generality in some integer n. So the polynomial q that minimizes this particular norm is called the nth OPA of g over f in LP. Now, existence of these polynomials is immediate because we're finding the distance from G to some finite dimensional subspace Fpn. Uniqueness is slightly different, but that's one of the reasons why I'm restricting P to not include 1 and not include infinity. In that case, we have LP being strictly convex, so we can automatically guarantee that this best approximation is unique. Uniqueness does not hold if you consider the case of 1 and infinity, which I'm not going to for the purpose of this talk, but there are a lot of interesting questions that you can ask in those particular cases. But at any rate, for the purpose of this talk, I want to now investigate this unique polynomial Q, which I'm denoting little q np fg. And the whole goal is to look at this polynomial and decide, well, is it also zero free in the closed disk? Just keep in mind, we're going to be using this, or possibly using this as a substitute for that denominator in the filter. So we want it to be zero free. However, what functions f and g guarantee that this polynomial is zero free, or which values of p? So that leads me to the second part of the talk, where I'm now concerned about zeros of these objects. So when is QNP FG zero free in the closed disk? And we already know part of this answer. At the very least, we know that if f is an H2, and we know that f does not vanish at the origin, Qn2 f1 is zero free in the closed disk. That's nothing new. That's just that result I mentioned previously from Chui and Chan from the 80s. So we're taking P to be identically 2, and or P to be 2 and G to be identically 1. So what I want to do first, start at this statement and try to generalize this as much as possible and see where I can go with it. So since we're, in this case, talking about H2, I want to then next move on to possibly HP. So just recall the Hardy space HP is the collection of analytic functions in the disk, so that, again, this supremum is finite, and that defines the norm on the function. And so I'm developing the theory in the context of LP, but I'm viewing HP as a subspace of LP by identifying F with its non-tangential limit function, which is in LP. But at any rate, so what I want to do is I want to generalize this statement above to the Hardy space HP. So the first thing that is concerning to me is why F does not vanish at the origin. Why is that a condition in the original statement? Is that something that we need to hold on to when we try to generalize? So that's the first thing, and the answer is yes, you do need that condition. So for any P, for any F in HP and any integer n, if your function happened to vanish at the origin, then that would guarantee the OPA is identically 0. So obviously that's not zero free in the closed disk. So we do need that condition. So when we generalize to HP, or at first when we generalize to the HP setting, we do need that condition. So our modified question is something that looks like this. If you have F and HP, and F is something that doesn't vanish at the origin, is QNP F1 zero free in the closed disk? So this is what we want to show. Showing it when P is 2 is not terribly difficult because we're in the Hilbert space setting. So we have tools such as reproducing kernels to make estimates on the zeros, but all that goes out the window in this case. But what we do have is the theory of sub-harmonic functions, which you can use. And in fact, you can show that for any given function f, all of the OPAs, at the very least, lie outside of some disk. So the statement is for any P, for any F in HP, again, that doesn't vanish at the origin, in any integer n, QNP F1Z is zero free in this particular disk. So you have, so first of all, I want to mention why this disk might be of interest. If you look at the radius, well, for one, it's not 0, because the only way it could be 0 is if the norm was 1, and that doesn't happen because the OPA Q0P is not identically 0, and that's because the function doesn't vanish at the origin. But also what I'd like to think that this statement says is that if you look at this norm, it's in a perfect world, that quantity is something small, you would hope. By definition, we're minimizing this norm. So you'd like to think it's something small. So I'd like to hope that what's underneath the radical is something that's, whatever it is, it's something closer to 1. So the essence of this theorem, it says something along the lines of, for any function f, all of the OPAs are zero free, at the very least, on most of the disk. So that doesn't answer the modified question, but it at least gives us a little hope. So going forward, my goal is to improve this estimate. And I've done some computations to make it so that I'm at least comfortable to state the following conjecture. So for any p, any f and hp, and any integer n, as long as the function doesn't vanish at the origin, you can conclude that the OPAs qnp f1 are zero free in the closed disk. So, like I briefly mentioned, what makes this conjecture more difficult is because we don't have the tools of the Hilbert space setting at hand. But however, if you restrict the value of p, in turn, you can use the Hilbert space setting to your advantage. So that's what I want to talk about in the third section. So what happens if we restrict p to be greater than or equal to 2? So in that case, it's not immediately obvious that we have tools of the Hilbert space to use to our advantage, but the following theorem suggests that we do. So if we restrict p to be greater than or equal to 2, f to be any HP function, and n to be any integer, then something happens. Either the OPA QNP F1 is zero free in the closed disk, which in that case, we're done. There's nothing to show. Other than that, we can at least guarantee that there's a function g in H2, which is zero free in the closed disk, or which is zero free in the disk, such that the OPA QNP F1 is equal to some OPA QN2 FGG. So our whole goal, going back to the beginning, is to study the zeros of QNP F1. That's not always so easy because we do not have Hilbert space techniques to use, but instead what we can do is study OPAs of the form QN2 FGG, and then in that case we have lots of tools to use. So then our new question becomes, when is QN2 FGG zero free in the closed disk? And the first thing I thought was that perhaps the function g has no bearing on the zeros. Maybe I'd like to think this OPA is somehow comparable to something of the form Qn to F1. But we're in the Hilbert space setting now, so computations are very easy to do. So after doing a few computations, I was immediately disappointed. So I have 3 examples right here that I computed. The first example, I chose 2 functions. I computed the OPA Q12 FGG, and I get something that has a 0 in the disk. So right off the bat, I'm angry. Example 2, same thing. I compute the OPA, and I have a 0 on the unit circle. Example 3, although the OPA is severely unattractive, it still has the properties that we're looking for, being zero free in the closed disk. So why is example 3 different from example 1 and 2? Keep in mind, we're exploring different functions g that are zero free in the open disk. but I say nothing about the boundary. So from these three examples, but also other examples that I've done, not necessarily with polynomials, but it seems to be that the behavior of the function g on the boundary is what's giving us the undesirable properties. So I'd like to at least state this conjecture. If you have two functions f and g in H2, and they have a little bit more structure, so you're assuming that they have continuous boundary values, so they could be polynomials, but you're also imposing the condition on g that it does not vanish on the unit circle, then that's enough to conclude that Qn2 FGG is zero free in the closed disk. And there's a lot of things I like about this conjecture because, one, we're in the Hilbert space setting, but it's interesting if we make some kind of headway on this conjecture, it can give us insight into the original conjecture that I'm trying to prove, and that's conjecture A. So if conjecture B is true, we know from that previous theorem that OPAs of the form QNP F1 have a equivalent form QN2 FGG. So this could, conjecture B being true, could give us insight into certain cases of conjecture A. And the whole purpose of conjecture A is to study the zeros of QNP F1 to see if possibly these polynomials could act as substitutes in the digital filter. I mean, so of course they're going to, if they are Bibo stable, in other words, if they are zero free in the closed disk, then yes, they could be used in the design process. However, they may not be feasible in engineering if you can't compute them easily. So computation is a whole other story, which I'm not going to talk about today. But if you are interested in computation, please have a look at the paper I recently posted on the archive. I do talk about that in addition to some other open problems and also the details of what I talked about today. But if you're interested in the engineering portion, I posted a couple of references. The first reference is a paper that Catherine Beneteau and I wrote a year ago, which talks about the design process implementing optimal polynomial approximants. And that's inspired by the third reference, which is one of my favorite papers, and that's the paper of Chui and Chan, where they originally showed that OPAs were zero free in the H2 context. But if you are interested and want to learn more about what I just said, the second reference is a paper that I recently posted. So have a look at that if you're curious. But that's everything I wanted to talk about today. So in the remaining time that we have, I'd be more than happy to answer some questions that you have.